So here's example 5. It tells you the binding energy per nucleon of lead, and then it asks you to work out the mass of this lead nucleus. So let's have a look at how we would do that. So first of all, we know that the binding energy per nucleon, or the binding energy per nucleon, is equal to 7.8751 mega electron volts. So we can work out the binding energy by doing 7.8751 multiplied by 206, okay? So if we do that, 7.8751 multiplied by 206, that gives us 1622.2706, and that is mega electron volts. Now we can then convert that into a mass. So we can work out the mass defect, basically, okay, because this binding energy here is the energy given out when the nucleus is formed, or it's the energy required to pull the nucleus apart nucleon by nucleon. Okay, so that's the mass. That's the binding energy. So the mass defect is equal to the binding energy divided by 931.5 MeV, and that gives you the mass defect in U. Okay, so it's going to be 1622.2706 divided by 931.5 MeV. Why is that the case? Well, because we know that 1 U is equal to 931.5 MeV. So if we find the number of times that 931.5 goes into this binding energy, that gives us the mass in unified atomic mass units. So we divide that by 931.5, and it gives us 1.7416, we'll just say, okay, U. Or it's probably best to use the full number, 1.741568. Let's just go to that number of significant figures. Now, because it's asked us for 5 in the answer. Now, we know the mass defect. The next thing we need to know is we need to work out the mass of the number of protons and neutrons individually that make up a lead nucleus. So we know that the mass number A is equal to 206. That means that the number of protons we know is 82 because we're told that. That means that the number of neutrons is going to be 124. Okay, so 124 neutrons. So the total mass of the protons and the neutrons individually is equal to 82 times 1.00728 plus 124 times 1.00866. Okay, so that gives us the total mass of the protons and neutrons when they're not combined together in the nucleus, but they're just on their own, so to speak. Whoops. Plus 124 times 1.00866. So that gives us 207.6708 U. Okay, so that's the mass of the individual nucleons when they're not combined in the nucleus. This is the mass defect. So therefore, the mass of lead 206 is going. The lead 206 nucleus is going to be equal to 207. Can't even write here. 207.6708 minus the binding. Minus the mass defect, okay? The mass defect, which is 1.741568. So it's the total mass of the individual nucleons minus the mass defect. That gives us the mass of our lead nucleus. So let's work that out. It's 207.6708 minus 1.741568, and that gives us 205.9292 U. Now to 5 sig fig, that's 205.93 U. And that makes sense because if you think about it, remember some of the mass, this amount of the mass, is converted into energy when these nucleons combine to form this nucleus. Okay, so that's example 5.